Hey guys, sorry I'm running a few minutes behind here. I was searching for an animation that I wanted to share with you, and I think you'll find it very helpful. So I appreciate you being patient. Sorry it took a second to get started. Let's jump right in. First things first. This week you'll notice the homework and the study guide are the same assignment, which is kind of weird. Basically, I didn't want to overload you. I know we've got a lot going on in this last week with exam 3 on Friday. And then the final, early the following week, you guys didn't need a new homework and a new study guide and a new test and all this other stuff. So the last study guide is going to come from the same assignment as your last homework. Basically what I did is I took the last homework, chopped it way down, and then added some problems so we can treat it as a study guide. So this assignment in WebAssign here, let me come back to that. This assignment right here, MAC2312 Study Guide 3 Fall 20, is also homework 14. It's got some new stuff, some polar and parametric stuff, but it's also got some power series stuff. It's got some arc length stuff. It's got all the things that you'll need for exam 3. And the rules are the same as always. In order to get credit for the study guide, you need to scan your solutions for this into Canvas. So as you're going through this homework, write out your solutions. As you're going through this assignment, write out your solutions, scan them, and submit them in Canvas like always. All right. So today, this is, of course, MAC2312, Section 2. It's the 30th. And we're going to talk about polar coordinates. Which in theory, everybody is supposed to be pretty comfy with coming out of trigonometry. There's a section at the end of trigonometry all about polar coordinates and graphing polar coordinates. Today, we're going to do everything that you did in trig regarding polar coordinates, just kind of a quick refresher. So we maybe spend a week learning how to graph things in polar coordinates in trig. We're going to spend one day going back over how to graph things. And then on Wednesday, I'm going to show you how to do some calculus operations in the polar coordinate system. All right, suppose I've got two people, so a little intro. Maybe Alice is here and Bob is here. And at the moment, perhaps they're both facing forward. So imagine each of them is like this, right? This works better when I have you guys all sitting in a class and I can point to one of you. If I wanted to tell Alice how to get to Bob, capital B, sorry, Bob. Capital B, Bob. I have two options, really more than that, but two obvious ways. First, I could tell her, okay, well, go to your left about yay far, and then go behind you about yay far. I could say go to the left X units and then go behind you Y units. All right, maybe units are feet or meters or whatever. Another option, I could tell her, hey, why don't you just like rotate around this far and then walk like that, right? I suppose I should tell her to rotate all the way around this. So the other option, if this distance between them here is r, I could say rotate theta, then walk r units. And in reality, it's the second one that we do, and we're giving people directions, right? I say, okay, head east 5 miles, or turn 45 degrees and then walk 10 feet. This is how you would actually tell someone to get, where's your friend? You're in the library and the buddy next to you is like, hey, which one of those people over there is this person? You say, oh, well, look this far to your left and then walk like 20 feet, or, look like 20 feet down the way. That's Joe, you wouldn't say, oh, go east 5 meters and then go north, 7 meters. You would say, rotate this much and then look about that far. That's the dude I'm talking about. So this system is the polar system. And it's the system that we are more comfortable using describing local spaces to each other. If I wanted to tell my wife where something is in the room, or if I wanted to get my dog to run somewhere, I would think of like rotate this far and then walk that far, not like go in these cardinal directions this far. So we want to do mathematics in that setting because it's a setting that in some cases is more intuitive to us, especially settings with a lot of rotational symmetry. All right, if you have a lot of rotational symmetry, then the polar coordinate system is your friend. So the red here is polar, blue is Cartesian. Just curious, anybody seeing this for the first time? Anybody's trig class not touch polar coordinates at all? It's okay, I'm just curious. You can give me a react there if that's the case. Any react, let me know. Okay. The problem with this system, and there are many problems with this system, just like with any system. The problem with this system is that coordinates are not unique. Okay. Yeah, I'm certain that not every trig class does this. Unfortunately, trigonometry here at Santa Fe needs some love, although they are supposed to. So formally, if I'm not talking about Alice and Bob, if I'm talking about a coordinate system, here's the XY plane that we're used to. Okay, all right. So pay careful attention then, especially if your trig class didn't cover this. Normally, if I wanted to tell you to get to a point XY, you would go over X and then up Y, yeah? Think of it like, here's Alice, here's Bob. You can go over this far and then up that far. Or I could say, starting at the origin, rotate up theta and then walk out this far. Okay. So I want to think about some things here. Let me kind of try to ignore this for the moment and just look at this triangle. This distance is y, right? It's the vertical distance of that point above the x-axis. This point here is in Cartesian coordinates x comma y. In polar coordinates, we would call it r comma theta. We always write the r first. And it's just two different ways of how to specify where this point is in the plane. I could say start at the origin and then walk over x units and then walk up y units. And that's the normal coordinate system. That's the Cartesian or rectangular coordinate system. Start at the origin, go over x, then go up y. That'll definitely get you here. Another option is to say, okay, along the x-axis, go out r units and then rotate up theta. That will also tell you how to get to that point. So a coordinate system is a collection of statistics that tell you how to locate a point in space. For us, the space is two-dimensional. We're talking about the plane. The system we're familiar with says to get to any particular point, you tell me how far over to go and how far up to go. That's the rectangular Cartesian system. The polar system says go out so far along the horizontal axis and then rotate up a certain amount, theta. So instead of thinking of it as x and y, over and up, you think about it as r and theta, out and rotate. Are we comfy with the core concept there? I can tell you how to get to a point by telling you how far out to go and how far to rotate. Now, the first thing we need is a means of going back and forth from one system to another. So converting from x, y to r theta and back. The trick here is to think about a triangle. This is a little right triangle. And if you look at the sine of theta, that's the opposite over the hypotenuse, which is y over r. So if you solve that for y, you'll discover that y is r sine theta. And similarly, the cosine of theta is x over r. That's the adjacent side length over the hypotenuse. And this implies that x is equal to r cos theta. So if I give you r and theta, these are the two things you need to tell me x and y. Right, if I gave you the polar coordinates, then you can plug in here to get the x and y, the Cartesian coordinates. Also, since this is a right triangle, this is x squared plus y squared equals r squared, according to Pythagoras. And the other useful relationship here is that the tangent of theta is y over x. So if I gave you x and y and I asked you for r and theta, these are the two relations that are useful for that. So this guy tells you how to go from polar into Cartesian. And these guys tell you how to go from Cartesian into polar. Both sets of relations can be useful for all sorts of things, but usually if you're going polar to Cartesian, you'll use these. And usually if you're going Cartesian to polar, you'll use these. Some people write this as theta equals the inverse tangent of y over x. That's very dangerous. That's not true. It's true only if theta is between negative pi over 2 and pi over 2. So the safer way to write this, the more honest and correct way to write this is this. And I'll show you what I mean about how that can be dangerous. But first, are there any questions where these things are coming from? Are we all comfortable with the origin of every one of these four little equations here? It's very important. See each other. Yeah, feels familiar. Okay, good, 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 good. I'm glad. I'm glad. Yeah, sometimes it's like an old friend, you know. At first you cross the room, you're like, who the fuck is that guy? And then you get close, like, oh, you got a haircut. You're like 20 years older, but I recognize you. All right. Let's take the dust off and see if we can't go back and forth. Okay, let's convert the Cartesian point. If I told you guys the story about Descartes, where Cartesian comes from, we call the rectangular system the Cartesian coordinate system because it was dreamed up by René Descartes, the French philosopher, the guy who famously said, I think, therefore I am. his greater contribution was the start of analytic geometry by putting points in a coordinate system. That's why we call this Cartesian. It's after Descartes. So I'd like to take the Cartesian point 2, 2, and put it into polar coordinates. So I'll always draw the picture. Always, always, always draw the picture. Picture is your friend. All right, so I'm going to go 1, 2, 1, 2. All right, here's the point. I want to find r and theta such that if I walk out this distance r and then rotate up this amount theta, I land at that same point. So in other words, I seek this distance and this angle. And the only thing I have are the relations that I showed you, you know, the x squared plus y squared equals r squared, tan theta equals y over x equals r cos theta, y equals r sine theta. So the useful ones, remember, for going from polar to Cartesian are x squared plus y squared equals r squared. And the tangent of theta is y over x. So let's start with this. This will help me figure out r. X and y are both 2. So this says 2 squared plus 2 squared equals r squared. That's 4 plus 4. That's 8 equals r squared. And this has two solutions. R could be plus or minus 2 root 2. Square root of 8 is 2 root 2. Let's take r to be the positive solution. That's the most natural thing to do. I'm thinking of r as a distance, right? So normally I would think of it as being positive, but it is possible that the radius here can be negative. Alex asks, can we infer that the angle is 45 degrees? So I'd say two things. First, always radians, por favor. I don't know what 45 is. I know what 45 degrees is, but I still don't like degrees. We really want to always be thinking in terms of radians. We can. It's true that the angle there is 45 degrees, or pi over 4 radians. And to get that, we use the fact that the tangent of theta is y over x. So here the tangent of theta is 2 over 2, which certainly is the same as saying tangent of theta is 1. And there's lots of angles that have tangent 1, but this angle should be in the first quadrant. It should be between 0 and pi over 2. So here it's true that theta is pi over 4, which is the inverse tangent of 1. Or 45 degrees if you want to put it in degrees. But we really, really want everything in radians, please. All right, so that's it, yeah. So the polar coordinates are 2 root 2, comma, pi over 4. That is to say, if you walked out here 2 root 2, so if you walked two root 2 and then rotated up pi over 4, so you walk out here 2 root 2 and then you rotate up pi over 4, that will get you to that point. This is r, this is theta. Remember, r always comes first. All right, everybody with me so far? Any questions about how we got this set of polar coordinates for this point? Let me try another one. So another example here. Same game, convert negative square root, let's do negative square root 3, comma 1 from Cartesian into polar. All right, so here's x, here's y. This time my x is negative root 3, 1. All right, so here's my point in Cartesian or rectangular coordinates. Again, I can draw the picture and say what it is I'm seeking, and that's helpful. So I'm seeking this radius and this angle.
Why? How do you know like you're not seeking the other angle per se? Like,
this is a great question. How do I know I want that angle and not this angle? The answer is you could use either, but the standard thing to do, right, just like in trigonometry, is you measure angles from the positive horizontal axis in the anti-clockwise rotation. So that's the standard orientation for measuring angles in trigonometry, right? As you start along the positive x-axis and you measure positive angles going anti-clockwise from there. But there is another way to do this, and I'm going to show you. You're actually a little bit ahead of where I'm at. Polar coordinates are not unique. There's more than one set of polar coordinates for every Cartesian point. But we'll get there. So hold on to that question for just a second. We'll come back to it. First, I'd like to find r. And I know that x squared plus y squared is r squared. So this means that negative root 3 squared plus 1 squared is r squared. The square of negative square root of 3 is 3. So 3 plus 1 is r squared. So r squared is 4. We could say r is 1 of plus or minus 2. We'll take r to be positive again. And so r here looks like it should be 2. And then theta. That relation tan theta equals y over x, that always holds. So here I get tan theta equals y, which is 1, over negative square root of 3. And I want to pause here just for a second because you do not want to take the inverse tangent to solve this. Be clear about that. If you take the inverse tangent to solve this, it will give you negative pi over 6, which is wrong, right? Negative pi over 6 is rotating like this. Nowhere near the shit I want way over here. I need to rotate like this, an angle that's larger than pi over 2. The inverse tangent function will never spit that out. So instead, you should be thinking about your unit circle. Where on your unit circle, for what theta value? That's a good question, Alex. R doesn't always need to be positive. It's just in these last two examples so far, I've chosen to take the positive value of R. But R can sometimes be negative as well, and that complicates things. I'm just building up to it. So the most natural thing to do is to take R to be positive, to think about it as a distance. But there are we will need to learn how to interpret r being negative as well. But let's focus on one thing at a time. So if the tangent of theta is -1/√3, and I know that theta needs to terminate in quadrant 2, what is theta?
Is it 5 pi/6?
It is indeed. And one of the ways you can see this is dividing top and bottom by 2. You can think of this as 1/2 divided by -√3/2. And then remember the point on your unit circle associated with theta equals 5 pi/6. All right, so one set of polar coordinates that works for this point. R comma theta is 2 comma 5 pi/6. And that's true. If you walked out here, 1, 2, you go out here 2, and then rotate that around 5 pi/6, it'll land you right there. Okay, I'll let you guys think about that. But that's not the only set of polar coordinates that works. Like Ayushi pointed out, what if I was looking for this angle, right? No, I'm not doing the voice to mock you. I'm doing it to like say there's this other angle right here, right? Instead of this angle, we could use this angle. What's the angle over here? If I wanted to rotate around this way, that would be pi plus pi/6. So another set of polar coordinates that could work is 2 comma -7 pi/6. These get you to the same place. Your theta is 5 pi/6, but we could also do 7 pi/6 just measured in the negative direction, right? Rotating clockwise rather than anti-clockwise. And believe it or not, those are not the only options. There's actually infinitely many ways to describe this point in polar coordinates. Infinitely many ways to describe any point in polar coordinates. Because I could also add 2 pi to theta, right? If I say rotate around here and then spin all the way around again, you're going to land back there. So I could also say 2 comma 5 pi/6 plus 2 pi, or 2 comma -7 pi/6 minus 2 pi. All of these will get you to the same stuff. In general, the infinite family here would be 2 comma 5 pi/6 plus or minus 2k pi. And it gets worse. Lads and ladies, it gets worse because there's one infinite family associated with the positive choice of r. There's a whole other infinite family of polar coordinates that you can use with a negative value for r here. So the next thing we need to talk about is how to handle the idea of r being negative. And before we do that, I'm going to back out of this example. But does everybody see how all of these, this whole infinite family of polar coordinates, take you to the same point? So just think of it one at a time, Eddie. If I walk out 2, so I walk out along my horizontal axis 2, and I rotate 5 pi/6, and then I keep rotating another 2 pi, do you see how that will land me here? So that's this guy. I walk out and then rotate my normal amount, but then I rotate another full rotation. So think of the safer path here is just think about full rotations. Don't worry about pi k or 2. So that we're not solving trig equations. You don't have to worry about that right now. That's not quite the same thing. It's true that when you solve trig equations, sometimes the thing you have to add on here are multiples of things other than 2 pi. It could be pi over 7 or something like that. But here, since we're talking about locating a point in space, we're really just talking about rotating whole circle rotations. So you can rotate around here and then all the way around and all the way around twice, all the way around 3 times. You could rotate up here and then rotate negative 2 pi or negative 4 pi. But those are fully encompassed by this family. Now, that's one way that polar coordinates are not unique, but it's not the only way. Another way that polar coordinates can mess your day up is by having a negative radius. So how do we understand the polar point r comma theta when r is less than 0? It's a challenge, right? R, when you think of radius, the distance should be positive. Doesn't really make sense to have r as negative, but it's not impossible. And I'm going to show you kind of, let's back up a little bit. I haven't formally defined polar system. Formally, polar coordinates describe this system. In the middle, there's the pole. And then poking off to the side here is what we call the polar axis. And when you think about the relationship between Cartesian coordinates and polar coordinates, the polar axis is usually the positive x-axis. And I say, okay, you want to get to some point up here. The way you do that is you measure your r. It's not sure it's like, yeah, it's about here. So you pick your radius along the polar axis, and then you rotate. In other words, you can think of the polar coordinate system as being made up of concentric circles. I'm a horrible artist, I'm sorry. And then once you've walked out some distance on your polar axis, you rotate up by whatever theta tells you to rotate. In fact, if you look at polar graphing paper, I'll hold here for just a second. If you look at polar graphing paper, it just looks like a bunch of concentric circles. I'll show you some. Here. Right, this is polar graphing paper. You have a circle for radius 1, a circle for radius 2, a circle for radius 3. So if I wanted to locate a polar point, sorry, I was playing around with some stuff here. If I wanted to locate the polar point, say, I don't know if this will work, 2 comma pi over 4. Yeah, there it is. I would go out to the radius 2 here. Oh wait, no, it's not. Sorry, it's doing this rectangularly. Never mind. So if I wanted to locate the polar point 2 comma pi over 4, I would come out here to 2 and then rotate up by pi over 4. And that would get me right here. That's one way to think about it. Now, we superimpose the XY axes here, then the Y-axis looks like this, and the X-axis looks like this. So I'm going to show you two different ways to think about R being negative. Let's locate or draw the point, polar point, -1, comma, pi over 3. Here's one way to do it. This is the way I was taught. First, you go out 1 on your polar axis. You pick your radius. Then you rotate up by the specified angle. In this case, pi over 3. (60°). Then you take that point and you flip it through the origin. So this guy right here is 1 comma pi over 3. That means that the point reflected through the origin is -1 comma pi over 3. So the point that I was asked to locate would be this guy. So to find the point -1 comma pi over 3, first you find the point +1 comma pi over 3, and then you flip him over the origin, or over the pole. Again, that's how I was taught to do it. But I've noticed another way of thinking about it that some students really seem to appreciate, seems to make things a little bit easier. That's why I'm happy to show it to you. Let's think about the whole circle of radius 1 here. What if I walked out sort of thinking of a negative radius? I walk out the negative direction along the polar axis. And then I rotated pi over 3 like this. That will also get you to this point, would it not? So you have these sort of two choices. You can first locate the point with the positive radius and then reflect it through the origin, through the pole. Or you can sort of think about walking out in the negative direction along your polar axis and then rotating theta. Both are equally valid. Okay. So if R is negative, that is indeed possible. That point will be symmetric with respect to the origin from the same point with the positive version of that radius and the same angle. The last sort of exercise I want to do here before we move on to graphing, really working in earnest, would be to say,
could you possibly go back to the other page real quickly?
This guy?
Yes, that one.
So sort of the two ways to find a point with negative radius is to first find the point with positive radius, then flip over the origin. Or instead of starting by walking out the positive version of that radius, start by walking out sort of in the negative direction along your polar axis. And then rotate. Either is valid.
Could you explain that problem again? Sorry, I was busy writing it down.
Okay, let's do these separately here. Two ways. to locate the point, let me do this time -2 comma pi over 6. One way, first find +2 comma pi over 6, then reflect through the origin, which in the polar coordinate systems is called the pole. So how do I find 2 comma pi over 6? First, I go out 1, 2 along my polar axis, and then I'd rotate up pi over 6. So, this right here would be the point +2 comma pi over 6. I'm trying to get to -2 comma pi over 6. And this says to do that, find this guy first, then reflect through the origin. So if I take this point and I reflect it through the origin, I'll land over here. So over here is the point -2 comma pi over 6. That's one way to do this. The other way is to walk out in the negative direction. On the polar, aka horizontal axis. Then rotate pi over 6. So what's that look like? All right, well, instead of walking out 1, 2 in this direction, I'm going to start by walking out 1, 2 in the negative direction. This is like arc -1, -2. And then I would rotate pi over 6, which will take me from here to like here. Oops, sorry, I should be using blue because I used blue up there. And you see, this gets me to the same point, right? It gets me to literally the same spot in the plane. So what we're trying to do is figure out how to understand polar coordinates when the r is negative. If r is negative, there's two ways to understand that. First, you can pretend like it's not negative. For example, if I wanted to find, sorry, this is negative. If I want to locate -2 comma pi over 6, I could first find +2 comma pi over 6 and then reflect it through the origin. Or I could walk out to the -2 instead of walking out +2 and then rotate my pi over 6. And you see this point and this point are the same. I get to the same place in the plane that I wanted to, just two different ways of thinking about it. Does that help?
Yeah.
So in both cases, my goal was to get to this point, right? Okay. So the last sort of exercise I would like us to do is, before we start graphing, is to find 3 representations of the Cartesian point let's do 0, 1 in polar coordinates. All right, so I want to find 3 sets of ordered pairs, r comma theta, that get you to the same point whose Cartesian coordinates are 0, 1. Right, so here's, this is y, and this is x. Here's the Cartesian point 0, 1. Right. Normal, old-fashioned, rectangular Cartesian point 0, 1. I would like to have one of them, well, let's have two of them with r being positive and one of them with r being negative. So how do I do this? Well, I know x squared plus y squared equals r squared, right? So 0 squared plus 1 squared equals r squared. This says r squared equals 1, so r is either plus or minus 1. Also, I know that the tangent of theta is y over x. So the tangent of theta is 1 over 0. Oh, this is a problem, isn't it? Well, what do we do here? This is one of these challenges, right? Where this way of thinking about things can get you in a little bit of trouble. So what's the angle here? It turns out the tangent of this angle is undefined. But we know that the radius is 1. And then we would have to rotate up some amount. How much do we have to rotate? It's okay that the tangent is undefined. What is this angle here?
Pi over 2.
Yeah, good. It's pi over 2. So this is one reason to always draw the picture. Okay, so my easiest set to write down, my easiest set of polar coordinates is 1, comma, pi over 2. Can anybody think of another set of polar coordinates that I could use where r is equal to 1? What's another theta value I could use instead of pi over 2?
Negative 3 pi over 2.
Very good. I could have rotated like this. All right. Now, r has to be plus or minus 1. So if r is negative, it has to be negative 1. Can anybody think of a way of expressing this point where the radius is negative 1?
Negative 1 and negative pi over 2.
Good. Because if you think about where 1 comma pi, negative pi over 2 is, if you go out 1 and rotate negative pi over 2, that's here. So if you then reflect that through the origin, you'll see that negative 1, negative pi over 2 is the point up here that we wanted. There's more ways, all right? There's lots more ways. There's infinitely many, but these are 3 of them. You could also have said here, negative 1 and positive 3 pi over 2. All right. If we went 1 and then positive 3 pi over 2, that would get us here, and reflecting would take us there. Okay. So I want to talk now about graphing functions. The easiest way to get started here is to think about constant functions. Like r equals a constant or theta equals a constant. Functions in general here, by the way, look like either r equals f of theta or theta equals g of r. Like either r is a function of theta or theta is a function of r. So your two kind of simplest families of functions, just like in Cartesian coordinates, you can look at like y equals a constant, y equals 1, y equals -2, y equals 5. Or you can look at x equals a constant, x equals 1, x equals -2, x equals 5. Those are in Cartesian coordinates either vertical lines or horizontal lines, right? Y equals a constant would be a horizontal line, x equals a constant would be a vertical line. Well, what does the function r equals 3 look like in polar coordinates? So this says, if you think of like a table, r and theta, no matter what theta is, r is always 3. So if theta is 0, r is 3. If theta is pi over 4, r is 3. If theta is pi over 2, r is 3. If theta is pi, r is 3. If theta is 3 pi over 2, r is 3. R is always 3. That's what a constant function is. So if I start plotting these points in the polar coordinate system, three comma 0. R is 3, theta is 0. That's definitely right here. 3 comma pi over 4. So r is 3, and then theta is pi over 4. And r is 3, theta is pi over 4. That's like, yeah. R is 3 when theta is pi over 2. That's like up here. R is 3 when theta is pi. That's here. And r is 3 when theta is 3 pi over 2. Okay, so if I start drawing all of these points, you notice that this forms a circle. Modulo my bad art. Big fat points. Of course it forms a circle. It's all the points whose radius, distance from the origin, is 3. Well, the collection of all points that are equidistant from some other point, that's the definition of a circle. So yeah, this is a circle of radius 3, centered at the origin. And r equals 5 or r equals 12 would all be circles of radius 5 or 12 or whatever centered at the origin. Another good example And there's only two possible examples. We're talking about constant functions. How about the line? I fucked it up. How about the function theta equals pi over 4? So again, I can make a table. This says, I don't care what r is, no matter what r values you plug in, like 0, 1, or 2, or -3, or -2, theta is always pi over 4. So here your table would look like this. I'm just picking random r's here, but now we can plot those points and see if we notice a pattern. All right, so let's say, like 1, 2, 3. So when r is 0, theta is pi over 4. Okay, well, if r is 0, I'm at the origin. If r is 1, then theta is pi over 4. So I come out to 1, and then I rotate up by pi over 4. That'll put me right here. This is the polar point 1, comma, pi over 4. If theta is 2, or sorry, if r is 2, then theta is also pi over 4. So that will put me right here. If r was -3, okay, 1, 2, 3, and then I rotate pi over 4, that would put me here. Or you can think of that as being the translated, the reflected point coming from the +3, comma pi over 4, which is also on the graph, because if r was +3, theta would still be pi over 4. So you begin to get the picture, right? -2. If we came out -2 and then rotated pi over 4, that would get me here. This is a line. This is a line through the origin, making angle pi over 4 with the polar axis. Okay. So those are your two simplest functions, right? Constant functions. In the rectangular coordinate system, constant functions are either horizontal lines or vertical lines. In the polar coordinate system, constant functions are circles centered at the origin and rays emanating from the origin. So again, your polar graphing paper like this, constant functions. Are these circles? And for whatever reason, Desmos doesn't like graphing rays here in polar coordinates. But like these sort of things. Yeah. So your constant functions in polar coordinates are circles centered at the origin and lines through the origin. The functions we're going to be interested in graphing, though, are considerably more complicated than these. So these are just warm-up examples. I want to finish today by showing you how to graph a couple different functions in polar coordinates. Unfortunately, we're a little bit short on time, so I'm going to have to move somewhat quickly. Here are the rules for graphing in polar coordinates. First, theta is pretty much always going to be our independent variable. To graph a function, r equals f of theta in polar coordinates, first sketch the graph in rectangular coordinates. Then transfer the graph piece by piece into polar coordinates. And I'm going to show you what I mean. So for example, I would like to graph r equals 1 plus cos theta. I'd like to graph this in polar coordinates. So first I'm going to draw the graph in rectangular coordinates, and then I'm going to think about what that means in polar coordinates. And the trick here is going to be to deal with, well, I'll just show you. So to graph this in rectangular coordinates, I have a cosine wave that has been moved up 1. Oh, and this rectangular coordinate graph always at least 0 to 2 pi. You can do more, but always at least 0 to 2 pi. So I'll mark this as 2 pi. Here is 1. Here is -1. This is my theta axis. This is my r axis. Oh, actually, I'm going to need to come up here further, aren't I? I'm going to mark this as 2. Sorry. That's ugly. Ugly. I just need more space. Sorry. So first, I'm going to graph this in rectangular coordinates. I just didn't give myself enough space on that graph. Yeah, it's going to be like this. So here's 1. Here's 2, because this is a cosine wave that's been bumped up 1. I find it helpful to draw this equilibrium line in here. I'll mark this as 2 pi. And this is pi over 2, and 3 pi over 2. We know cosine of 0 is 1, so when theta is 0, r is 1 plus 1 up here at 2. Cos of pi over 2 is 0, so that is 1 plus 0. Cos of pi is -1. Cos of 3 pi over 2 is 0. Cos of 2 pi is, again, 1. So this graph looks like this. Right, here is the graph of 1 plus cos theta from 0 to 2 pi. I think we should all be comfy drawing that graph. This is the rectangular coordinate graph. Now here's the trick. To transfer this graph into polar coordinates, you have to imagine a little arm rotating around. And as this little arm rotates around, there's a guy running in and out along the arm. If he's out here at the very end, that's r equals 2. If he's right here halfway, that's r equals 1. If he's all the way in here, that's r equals 0. He runs back and forth, and as the arm rotates, he runs around on it, tracing a curve. I'm going to show you a little animation. The blue and green thing you see moving around here, that's your arm. And the red curve that's left is the guy running back and forth along the arm tracing. Here's a slightly simpler example. see if I have any other simpler examples I can show you here. I don't think I do. No. No. Okay. So here's what we do. If my arm hasn't started to rotate at all, theta is 0, then r should be 2. So let me mark off some lengths here. Let me call this 1, call this 2. So when theta is 0, the arm hasn't rotated at all yet. My dude is all the way out here at 2. So here's my first point. That point is coming from this point. As my arm begins to rotate up, right, here would be theta equals pi over 2. Here would be theta equals pi over 4, pi over 6, and so on. As my arm rotates up, theta equals 0, pi over 6, pi over 4, pi over 3, pi over 2. What is my little guy doing? Well, r here is decreasing. And it decreases, by the time we get to pi over 2, it decreases from 2 all the way down to 1. So my little guy is running in. And by the time we get up here to where theta is pi over 2, r has decreased all the way to 1. So again, I'm going to rotate the pen, watch my finger. What kind of curve did that trace? Well, it came up here tangent, and it arrived in here like this. So it's something like that. This is the pen rotating from theta equals 0 to theta equals pi over 2. And the place on the pen where the curve, the pencil curve intersects the rotating pencil, that is r. So here r is 1. This distance is 1. Here r is 2. That distance is 2. And you can watch that distance shrinking as we rotate through here. That corresponds to r shrinking from 2 to 1 here. As we continue to rotate past pi over 2 towards pi, r is shrinking still. It's shrinking from 1 all the way into 0. So if I were to look just a little bit past pi over 2, right, maybe to 3 pi over 2 here. I'm sorry, not 3 pi over 2. To 3 pi over 4 here, r will have come in just a little bit. It'll be a little bit smaller, right? Maybe here's 3 pi over 4, whatever, 2 pi over 3 or something. Here's the arm at 2 pi over 3, and the radius has come in a little bit from 1 down to 1 plus the cosine of 2 pi over 3. So it'd be in just a little bit. And as we rotate a little bit further, it will come in more. And by the time we are facing like this at pi, we should be coming all the way into 0. So this will draw a curve that looks like this. And again, you can kind of imagine just rotating this, picture the little guy running in. R is getting smaller, 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 smaller. And by the time we're down here, R is 0. The symmetry in the graph from here to here corresponds to a symmetry here. As we rotate past pi towards 3 pi over 2, r is going to be poking back out again. By the time we get to 3 pi over 2, r will be 1. It's a little too big. It'll be something like this. And then it will come back around and connect up over here. This shape is called a cardioid. And the trick to drawing this really is to think about that rotating arm and imagine a guy running in and out along that arm as he rotates around. Some points that we could check along the way, like when theta is pi over 4, when the arm was here, we have the polar point cos pi over 4 is root 2 over 2. So this is 1 plus root 2 over 2, comma, pi over 4. The polar point up here is 1 comma pi over 2. The polar point here was 0 comma pi. Down here, this was 1 comma 3 pi over 2. And if you want, you can look at the point over here. This is when theta is equal to 1, 2, 3, 4, 5, 6, 7 pi over 4. And theta there is again 1 plus root 2 over 2. So this shape is called a cardioid. I encourage you to download or look at some polar graphing paper. It'll make sketching these curves a little bit easier for you. You can print some of it because it has your angles and radii labeled for you. Please do not work with the degrees one. Please use the radians one if you're going to do this. It's a good way to help you train that if you haven't already got it in your head. And yeah, I'd like to, let's see how we're doing on time. I'd like to run through another example or two, but I fear that we are, out of time for today. So next time I'm going to show you a few more examples of polar functions plotted in polar coordinates. It will take some practice to get comfy with it, but you will eventually get comfy with it. Some fun ones that we haven't looked at yet are like r equals sine 2 theta. Or sine 3 theta, 4 theta, 5 theta. There's some neat connections between the angular momentum and the number of little loops on the graph. The family of curves we just looked at, like 1 plus cos theta, in case you're nervous, here it is, sketched by Desmos. These are called cardioids. You might ask, what happens if I change this cos theta to a 2 cos theta? Then you get a little inner loop here. If I change this to a 0.5 cos theta, then we never retract all the way in. What if I just had r equals cos theta? Well, then you would get a circle. So I'm going to show you guys some more of these graphs next time. Please do get working on that homework. There's plenty of stuff in there that is review meant to help prepare you for the exam on Friday, some power series stuff and some arc length stuff. But I recommend right now jump to the polar problems, right? Right now, focus on doing a little bit of the polar stuff between now and Wednesday. Then between Wednesday and Friday, you can focus on reviewing and finishing up the early study guide problems. When you hand in your study guide, it's okay if not every single problem is done. I know that the assignment here is a longer one than you're used to for study guides. So my recommendation is do all the stuff that you want feedback on and submit that. And I'll go through and check each day between now and Thursday evening for stuff that's submitted, and I'll try to give you a little bit of feedback before the test. And then once you finish it all, even if it's after Friday, as long as it's before the final, once you finish this assignment, go ahead and upload the final version of your solutions. Remember, to get credit for the study guide, you have to upload to Canvas. All right, you got to come over here to assignments and upload for study guide 3, your work. All right, that is it, guys. I'm gonna let you go here. I hope you have a lovely rest of your day. You can come see me in office hours, or you can send me messages on Canvas or through email if you want to talk more. I wish you all nothing but the best and a lovely rest of your day.